Hey everybody, today we'll do another problem. And today we will, I think this is going to be the last problem in this power factor and capacitor area of the book. So, um, so yeah, so we have a problem. It says that a balance, I need to find one that works better. A balance, a balance about a three-phase positive sequence, positive sequence positive sequence source source B A N equals 120 degree with an angle of 0 degrees. I'm sorry, 120 volt, right? Sorry, 120 volt with 0 degree, right? So 60 hertz connected, all right, and it says connected okay, so let me just put everything 60 hertz, right, is connected to a three-phase Y connected to a three-phase Y connected load that consumes 375K 375 kilowatt at 0.85 power factor lagging, right? So lagging, right? Oops, lagging. What else says? It says calculate the required per phase capacitance of the balance load, right? So calculate calculate the per per phase per phase calculate the per phase capacitance of the bat. Okay, capacitance capacitance of the Y connected capacitor Y connected capacitor bank. Okay, so we seem like we have a lot of information here. Okay, capacitor bank. If the power factor need to be improved, right? If the power, if the power factor needs to be improved. If the power factor need to be improved, right? So notice that we have some keywords here. To 0.95, right? So last video we did not have this, right? We did not have the power factor, the two of them. Now we have the two of them, right? So now we're looking for something else. We're not looking for the power factor. The two power factors are given, right? Power factors, you can call this A or B, whatever, or one or two. Doesn't matter how you call it, but as long as you recognize that this is power factor old and this is power factor new, right? Because those angles are going to be different. So notice that the angle for this is going to be bigger and the angle for this is going to be smaller. The better is the power factor, the smaller is going to be, it's going to be the angle getting almost to zero, right? If you have just pure resistive load, you don't have no angle between there's no angle. So therefore that would be that would be 100%. That would be like, one power factor would be perfect. But obviously, reality doesn't work that way. It doesn't work that way. So that's why we have this power factor that varies, between 0 and 1, right? So now notice that we have another here, right? Another thing to recognize, right? So we have there's a three-phase system. And it's Y connected, right? Very helpful. That's Y connected. And they ask them for per phase, right? Capacitance. They're looking for the per phase capacitance, right? But notice that we have what? We have something like this, right? We have a VAN, which if you watch my last video about what that is, this is something like this. So, like that, right? And then you have your Y connected system like this, and you have like um, you know, A, V, and C, right? And notice that between this phase from V to C and from C to A, we have we have we have 120 degrees, right? We have 120 degrees in this. Now, something is very important over here to understand that they give us, right? So let's say, for example, they're already telling us that it's a Y-connected system, which mean that there is 240 volts from here. I'm sorry, it's another. It's not 240, right? So it is a voltage between over here that is going to be greater than the middle, right? In the middle, if you remember, in a Y-connected system, um, we have something in the middle, right? And especially in the Y-connected system, we have something like this, right? So, and this one is called what? It's called the neutral, right? So, which this one is called, also is called BAN. This is the one given to us, right? So notice that if there is 120 volts, right? So if there is well, first of all, let's figure out which one it is, right? If it is a three-phase, what do we need to do, right? They telling us that this guy right here is 120 volt angle zero, right? If this is 120 volt angle zero, this guy, right? That means that I have to multiply by the square root of 3. If I take that number, if I take 120, right, times 1.732, it's actually between this and this, right? Between this and this is actually the voltage across, right? Because if I want to, let's say, for example, right? So if we want to find the voltage between this and this, what do I need to do? I need to say, okay, VBC, right, is equal to what? Is equal to 120 volts, right, times the square root of 3, right? Now, why? Because it's a three-phase system, right? So what I do, when I do the math over here, this is BC is equal to what? Right? This is nothing but 208 volts. Very close. Not exactly, but very close to 208. Now, this guy right here, so that mean that from V to C is 208, then from C to A is going to be 208, and from A to V is going to be 208, right? So this was kind of a tricky question. What they want to test us is how much we know when they say it's a Y-connected load, it's a three-phase, right? Now, because we need this number, we need this guy to do the rest of the calculation. So now we use the neutral, right, to calculate the phase voltage, right, phase to phase, right? And then from that, we actually got the you know, I mean, and let me you know, I don't want to confuse anybody. When I say phase to phase, it's like if you put the coil, the meter between the two coils, right? But if I say, if you have something like this, outside outside, going outside like this. This outside, this would be line to line. This is called B line, right? This is called B line. So B line between the lines, right? And B phase between the phases. So in this case, the line to line will be like this, right? Because the line to line from B to C is going to be like this, right? So like this, right? And of course, right? So this is A to B, and then B to C, of course, is going to be like this, right? But I just want to make it sure that people don't get confused. When I say line to line, I'm talking about face to face, but outside. That is line to line. But if I measure it be coil to coil, it's going to be face to face inside the transformer, inside the transformer coils. Okay, so basically we got this, right? So we have a B phase, right? So we have a B phase that is 208, right? Let me put this right here. B, you can put it BAV, whatever. BAV equal 208. The same thing. Like I say, that is, I just put that for alphabetical order, but it doesn't matter. This phase is sort of the same, face to face, right? So now, let's do it. Okay, so they're telling us that they're giving us some numbers, right? So we found this guy, right, using that one. And this is about problem solving, like I previously said, right? You need to be think about it. Okay, what is given, right? Well, it was given yet, but I'm not going to use directly this 120 volts because it's VAN. VAN is the neutral, right? So the neutral between line to neutral is 120 volts. Between line to line or face to face is 208, right? Now, this is important. So we have what else? We have this, right? And we have these two guys. Now what I will do is I can say that C now, right? C is equal to what? It's equal to power. Okay, another thing that I noticed that is important to understand is that they're giving us this guy, right? So when it says consumes, right? Consume. If an equipment consumes power, it does not consume the imaginary power, like it doesn't consume the VA, it doesn't consume the K bar, right? It doesn't consume reactive power, right? It doesn't consume apparent power, it doesn't consume reactive power. What it does, it consumes real power. So this is a real power, right? This is a real power. So therefore, we need to use the formula that is called a P, right? C is equal to P. And then inside the parentheses, we put tangent of theta. Normally, we put the tangent of theta nu. Let's see. Yeah. So tangent of theta nu, actually old. We can say 1 or 2. Minus tangent of theta 2, right? Now, in here, we need to do something, right? The bottom we have to divide it by omega V RMS B squared RMS. And what is B squared RMS? Well, we found it. That is the line to line voltage. of phase-to-phase voltage. So we found that one. So we need to do omega. Omega, we say that is 2 pi f, right? So omega in this case is going to be 2 times pi times 60 hertz, right? Now, when we do that, but then the first step is to find data 1 and data 2, right? Well, data 1 is the first one given, which is this guy, right? And data 2 is the other ones, right? So how we do that? Well, we know that power factor, right? Power factor equal to cosine of data, right? Now, the inverse of that is data equal to cosine inverse of the power factor, right? Okay, so cosine inverse of the power factor, if I take the inverse of 0.86, 0.85, so if I do that, it's equal to 31.779. So 31.8. It's equal to 31.8, right? Degrees. Okay, 31.8 degrees, right? Right, 31.8 degrees. Now, notice that we have a 31.8, right? That's data 1, right? Data 2 is going to be equal to this guy, right? Which is going to be cosine inverse of what? Of 0.95, right? When I do that, this is, right? So when I do that, that is 18.19. See, I told you that the angle of this is going to be lower, right? So notice that over here we had 90, right? The power factor for this over here was 90, right? Actually, it was 85. In this, the power factor was 90. Just by increasing the power factor, the angle reduced down almost a half. So this one is 18.2 degrees. So now I have a data 1 and I have a data 2, right? So we know that this is the formula. So let me just do this right here. So cosine, okay, so data is equal to cosine inverse of the power factor, right? Of the power factor. So I can put the 85 right here so you can actually see 0.85 is equal to that guy, right? Now that we have those numbers, pretty much we have everything. We have everything what we need, right? So I can say that data 1 equal to 31.8 degrees, and data 2 is equal to what? Is equal to 18.8 0.2 degrees. 0.2 degrees. Okay, so now that we have that, Now that we have that, we can apply this formula, right? So, so we know that this is the formula, right? That we're using. So let me just write it down here. So I need some more space. So omega is equal to 2 pi f. So omega is equal to 2 pi f, right? And then, right, and it's omega is equal to 2 pi times 60 hertz, right? So, okay. So when we do that, what do we get, right? We get the following. We got C is equal to what? C is equal to power, right? Which is this guy. We have that one. So it's 375, right? 375. No. 375 times 10 to the third, right? Times tangent of data 1, which is data 1 is 31.8 minus tangent of data 2. What is data 2? Is 18.2. 18.2. So parenthesis, right? The bottom over here, we have something, right? And the bottom over here, we have this, right? So we have omega. And when we do the math over here, we get that. Matter of fact, let me just write it down first. So right here, right? So we have 2 pi times 60, right? 2 pi times 60, right? Times what? Times that guy, right? And it's going to be a square, which is times 208, 208, right? And it's going to be a square, right? Now, when I do that, it's the following. So when I do that, the top, remember that this number, right? So this number is going to be big, and then this number is going to be kind of small, but it's going to be enough, right, to multiply this by, something big, right? So this is going to be multiplying that, but this is going to be a small, so divided by a big number is going to be small, right? So let's do it. So right here, C is equal to what? It's equal to 300,000, right? 375, right? Right? Now, right here, we have what? We have this, right? But then when I do the math on that, just let me do it. So tangent of 31.8, right? Is 0.62. So this guy right here is 0.6200, right? Then minus that guy, right? So then tangent of 18.2 is 0.3 minus 0.3, 0.328. Right. Now, analyzing this, right? What is going on here, right? So So now we do the mathematics for that one, and that is pi, 2 pi times 60 times 208 squared, and that is a big number. That is 16,310, 16,310, 1 3.75, right? Now what you do? Well, just do that, right? So now what we do? Basically, we have the numbers. Piece of cake now, right? So 0.62, right? 328, right? Times 375, 0, and then we take that and divide it by 16, 143.75, right? And we got something is very yeah. So basically, yeah. So 208 squared, right? Times 2 pi. Okay. So I think this is a little different number. Okay. So I guess when I did this, I think I had the answer for something else, but this number is a little different. So okay. So let's do this. Let's do this again. So we get the right number. So 208 squared. 208 squared times 2 pi, right? This number should be 27. See how the difference is going to be? It's going to be adding another zero to the left. So 27, 1835, right? Now, when you do that, when you take 375, 000 times 60 times 6200, this is 0.6200 minus 0.328, right? Then that is equal to 10, 9, 5, 0, 0, right? In the bottom, you got 27, 1835. That's interesting. That's interesting. Okay. Do I have to follow the order of operations? 109500 divided by 271835. That's interesting. Okay, so let me do something right here, because it seems like this is not, which is weird. Because that's technically that's the way that it should be done, right? So now let me try to do the whole thing in one shot. So 375 000 times tangent of 31.8 minus tangent of 18.2, right? Everything divided by 2 pi times 60 times 208 square. Okay, so C should be equal to, at the end of the day, and thus you got to be careful with this calculator, because they don't give you a lot of options. But at the end of the day, the answer for this is the following. So when you have this number right here, right? So plug everything in the calculator, and you get, as long as you put in the calculator as it is here, you add 3 zeros, put it like this. So C is equal to 0.00669, right? If you move this 1, 2, 3, that is a milli. You can, because it's a big number, but the books laugh like that, which I don't care. You can make this a microfarad too. You add 6 places, to the right. But I guess it's closer to the millifarad, so the way that they did it. So, but either way, right? So this is nothing but when you do that, right, and you round this up, this is nothing but 7 millifarads, and that is the size of the capacitor that should be that is the size of the capacitor that should be connected to this load to increase the power factor to 95, right? So that is the size of the capacitor. Okay, so that's it, guys. I hope this helped anybody who was taking the circuits. Thank you for watching. See you in the next video. Thank you for watching.